So what is good about the Mach-E crypto system? Of course, has like some good features and some bad features. And the good features are obviously that, for example, the encryption process is very fast and straightforward. Because all you're really doing is, for example, for Mach-E, a matrix vector multiplication, and then you just like some flipping some positions. That's the error. In the case of the writer, it's really just like a vector matrix multiplication. You're just computing a syndrome. There is the extra complication, if you want, of embedding your message into like this fixed weight string, but there is something that can be easily addressed. Okay. What is bad is primarily that the public key tends to be very, very big. Okay. So even with Mach-E's original parameters, which right now are kind of like a weaker security levels, you already get something like 65 kilobytes of key. And basically the reason is that the matrix is a quadratic object in nature, and therefore there's really not much you can do if your object is quadratic and you have to have a certain security level. Then it's going to grow very quickly. So a big part of the research over the last few years was primarily trying to address this concept, and the first idea was to use a variety of different classes of codes that may offer like different features, but like a lot of them revealed to be too easy to recognize. And then towards the years 2008, 2009, or maybe like as back as 2005, people started investigating a different idea, which is very clever though, and it's that to use structured codes. And so what do you mean exactly by structured codes? Because it looks to me like, hey, codes are already structured enough, right? So what I mean by structured codes is that you're putting some sort of additional geometric properties on top, okay? So at a high level, let's look at the area. Suppose that your matrix, you have this public matrix, and you have to communicate all of it, right? So there's like k by n bits. K is about n half, so it's about n squared bits or k squared bits. Anyway, it's like a quadratic thing. Now, suppose that I was able to actually represent the matrix in a compact way, then of course I would save a lot of bits. Right? For example, if you have a cyclic code, we haven't really delved too deep into cyclic codes, but you know that cyclic codes look like this. They have a generator matrix which is like g of x, and then like x g of x, and then like x squared g of x, and so on, right? Yeah. And basically each row is like, this is my row, and then I have like a rotation of it, and then I have another rotation of it, right? Mm-hmm. So it's what is called a circulant matrix. So obviously, if your matrix is circulant, you don't need the entire matrix to be published, because you can just produce the first row and then regenerate the other ones. And in fact, what is interesting is that you can actually map, and we will see this in a little bit more detail, but you can actually treat this as a polynomial ring, right? And then when you're computing a matrix vector multiplication, you don't even need to produce the entire matrix, because you're just multiplying two polynomials together, right? So, so that is a neat idea. That's the base of it. Now, of course, there's two problems here. How do you ensure that your public matrix is still in this form, right? So you can start from a matrix in this form, but then as soon as you choose, because remember, for example, you start from a G, and then you do SGP, and so your scrambling matrix S, your invertible matrix on the left, is going to mess up things. It's going to be a linear combination of rows. And your permutation matrix is certainly going to move all the columns around. And so can we do this in a way so that the public matrix still retains this structure? And the answer is yes. And the second question is like, just how much structure can we put? Because if the matrix is entirely circulant, then it's a very big reduction, but it's very easy. At the point, you just have to guess one row. Mm-hmm. So what we mentioned last time is that there's two pillars in security. One is like, it's hard to decode if the code looks random, and this is we can pretty much rely on this. But the previous one is your code actually needs to look random first. And if it doesn't, there's this kind of family of structural attacks, and they're trying to extrapolate the private code from the public one. So it looks like if you choose a fully cyclic code or cyclic code, it's just too much. But let's see if we can do something a little bit safer. Okay, and before we move on, I just wanted to pinpoint this. So essentially, what you can do with cyclic codes, because you have this structure here, you can identify them if your code is defined over FQ with the ring FQ to the X modulo X to the N minus 1. Okay? And therefore, your code words will just be polynomials. Everything will be polynomials, and you can imagine that your matrix G is really just a polynomial G of X. And then when you multiply, you're just doing all the shifts. That's exactly what the multiplication is, modulo X to the N minus 1, because modulo X to the N minus 1 means that X to the N is equal to 1. So your polynomial will never go above degree N minus 1, right? And that's exactly how the multiplication works. We saw it last time. When you multiply by X, you're shifting everything by one position. When you multiply by X, okay. So that is what we had for fully cyclic codes. So now we can try to do one thing that is one of the most important things in mathematics. So what you can do in mathematics is often like take a notion and generalize it, or take a notion and like weaken it, relax it, how we call it in mathematics, right? And in this case, what we're going to do is move from cyclic to quasi-cyclic. And the word quasi from Latin means nearly or almost, and that's exactly what's going to be. So they're not going to be fully cyclic codes, but they're going to be quasi-cyclic codes. But what does it mean to be a quasi-cyclic code? Suppose that I have my length n, here is capital N, and that's certain n0 times L, okay, and then I have a permutation by L that permutes the elements from 0 to n minus 1, but this is not just any permutation, because if I take any permutation, it's going to mess up my structure. So the permutation I want it to be defined by orbits, right? 0 up to L minus 1, and then L up to 2L minus 1, all the way to N0 minus 1, L until the last element. So the permutation acts on blocks of L elements at a time, and we say that the code C of length n is quasi-cyclic if it's invariant with respect to pi L. Okay? So if I'm able to define a permutation, it doesn't just move all the elements randomly around, but it moves like the first L together and then the second L of them together, and so it's block permutation. Then the code is quasi-cyclic. Okay? So basically, we admit a code which is not fully circulant, but is block circulant. So your matrix will look like this, for example, where each block is L long. Okay? And then when you apply permutation, you see that the permutation will permute these columns within themselves, and then these columns within themselves, and then these columns within themselves. Okay? And if I apply such a permutation, and my code is invariant, then the code is quasi-cyclic. So this looks like exactly what I want to do. Okay, so basically, I don't want to go too much into details, but essentially what you can do is you can start from, for example, a Reed-Solomon code. This was an idea by Berger, Cairel, Otmani, and Gabori. And the idea is, suppose that I start, for example, for a Reed-Solomon code. We haven't defined this, right? But we have said this is kind of like a generalized version of the BCH codes that we did look in a little bit more detail. So it's one class of algebraic codes, right? And we take it of length n, exactly equal to n0l. And then we take a parity check matrix, say U, that is made of blocks A0 down to A n0 minus 1. Okay. Then we can, so this is like a larger code. And remember, this class of codes, like the BCH codes, for example, or the GOPA codes that we did talk about for Michaelis, they rely on, for example, choosing a support of elements, right? Mm-hmm. And then applying some properties, like, for example, for the GOP, you have a support and then a polynomial such that the support is not roots. And so that's kind of like generally the thing with these algebraic codes. So we have here a bunch of blocks. We have n0 blocks. Each of them is like L elements. We don't need all of them, so we can, for example, select just little n0 blocks, where little n0 is less than big n0. So we only select some of them. This adds some randomness to the key generation process, which is kind of what we're describing right now, right? And then we can say we can rearrange them in a certain order so that we get a new parity check matrix, which is like A J0 all the way to like A J n0 minus 1. So we take some of these blocks, rearrange them. Okay, we're kind of trying to hide the original structure. And then what we can do, we basically multiply by a diagonal matrix D. So if we do that, then we scale some of these blocks. We just have a scaling factor in each of them. And then we do, so this, all this, we start from a field FQ to the M, so an extension field, and then we're going to project this onto FQ. So we just take only the QR rewards, which again is something that I mentioned before that we did for GOPA codes, for example. So we restrict to a subfield. Okay. And okay, at this point, a standard technique to do this is once you have an element, say alpha, which is going to be, actually, you know, this is going to be like, if alpha is primitive, this is going to be like set alpha to the j in the field, right? Or if we want to restrict to the subfield, what do? We can write alpha in its basis over FQ, right? So suppose that I have, for example, f2 to the 4, and I have a certain element, alpha to the j, right? I can write this as like 1, 0, 1, 1, which is this binary expansion, right? And then my matrix, instead of being a R by N matrix, I take each element in my matrix and it becomes its expansion, right? Then I take this other element, it becomes its expansion. Then I have another element, it becomes its expansion, and I explode the matrix, right, in this way. So it becomes Rm by N, right? And now this matrix is all on the subfield. So this defines the subfield subcode. So from a parity check matrix of the upper code, with all the code words, I can get a parity check matrix of the subfield subcode by just doing this kind of projection thing. And this is what you do here in the end. So you start from a big code, you select some of its blocks, move them around, scale them with the diagonal matrix, blah, blah, blah. In the end, you take the restriction to the subfield subcode, and this is going to be the public one. Okay. Now, every operation that we did through here preserves this circular structure, right? So if you start with your Reed-Solomon code in quasi-circulant or block circulant, then the matrix that you have in the end will still be block circulant. Okay? And so the process is quite convoluted, but you get the idea that is, in fact, the key generation is the most important part. Because what you end up with is going to be a parity check matrix H, which is of this form, which is a parity check matrix H for a subfield subcode of a permuted scaled version of an initial Reed-Solomon code. So now you can use this one as, for example, a public key if you're using it a writer, or you can get G from it and use it in Michaelis. Remember that once you have H, you can always get G. If you have nothing else to do, the worst thing that can happen is you just stick it in systematic form and then get G from the systematic form, right? So, so this is a good example of how you actually create a trapdoor in a bit more convoluted way, clever way. So there's a bit more work behind this, okay? So now the advantage is that my H is going to be exactly block circular. And so then I don't need to give the entire matrix, but I can give just the first row of each block. Okay? And in fact, what happens by analogy is that basically this is going to be also in this kind of ring structure, but then the length is going to be just the length of each block rather than the full length. Okay? So hopefully this makes sense. The basic idea is that how can we reduce the storage required for the public key? We want our public key to be in a form that is possible to express compactly. And how to do this is actually not obvious, because these codes have to satisfy a lot of constraints already, right? For example, Reed-Solomon codes like BCH, like GOP, and all these class of codes that are related, they are based on certain properties, intertwined elements, certain polynomial that has to satisfy certain conditions, and blah, blah, blah. So you start from one of these, and then you carefully select your transformation so that it preserves the structure, okay? Now, is this still going to look random? Well, of course, it's not going to be random because it is block circular, right? But you can claim, this looks like if I just took a bunch of random circulant blocks, right? So it's random among the matrices of the same shape, if you want. This is the assumption, okay? So if you get to do this, for example, here's some example. Remember we talked about Michaelis. Michaelis used the 1024-524, right, or binary code. So here what you can do, for example, is you start with q to the m equal, for example, 2 to the 16, right? And you start with the circulant order 51. You start with 1285 blocks, right? And then you select something like, I don't know, 9, 10 of them. This leads to different parameter choices. Okay, so you start with like a big full code, and you select only like a small amount of them, so it gets you to like a much shorter, right? So there you get that, like there's a lot of uncertainty there. And so, for example, if you choose 9, that leads you to a code that is 459 long. You just multiply 9 times 51, and then the dimension is 255. So first of all, the code is much smaller. It's already half of the one used by Michaelis, right? Because there was 1024. But also, it's circulant of degree 51. Right? So you have only really like, so you can divide by that. And you are going to project this over 2 to the 8. So you're going to treat this as a quadratic extension of f2 to the 8. You can play with this parameter. Michaelis was doing starting from f2 to the 8 all the way down to f2 binary. Here you just do it a smaller degree, but you can see that you can play with this parameter as well. And this leads you, for example, to a key size that is only 8,000 bits, which is about like 1 kilobyte. Okay. Now this is like the weakest one, but there's like, of course, when you do this work, then you propose some parameters based on these observations, and so you can calculate exactly what the size of the matrix is going to be, like n times k, blah blah blah. Okay. All right. So this was one idea. That was not the only idea. There's other types of transformations that you can do. Another one that is interesting is this. So the cyclic codes, we kind of already have the intuition of how they work. We take cyclic, but it's too strong. We immediately take like quasi-cyclic, and it's going to give us a nice result. So here's another idea. There is a transformation which is called dyadic. And so this is another way, if you look at it the correct way, of just being invariant under a certain type of action. Okay. So what is a dyadic matrix, first of all? if we have, say, a vector h equal h0, hm minus 1, a dyadic matrix is symmetric matrix, and the let's call it delta of h. This is defined by h, and its ijth component is equal to the element I XOR j of this, which we call the signature. Okay, so signature defines the matrix, and the matrix, it's gonna select in each position, right, the element I XOR j. So you treat the indices as binary. So the first position will be h00, which is the first element of the signature, and then like you start like, but you can see already that the matrix is symmetric, and the XOR is obviously symmetric, right? Because I plus j is the same as j plus I. So the matrix is going to be symmetric. It's going to have a form of this. This is much easier to understand. It's going to look like this. And then recursively, each of these blocks are going to be themselves of that form. Okay, so if you choose a power of 2 as the length, then this is going to be CDDC, EF, FE, EF, FE, CDDC, right? And then each of the C, D, E, and F are themselves. Right? So you can start with, say, like single element, and then like do little 2x2 blocks, and then they become 4x4 blocks, and then they become 8x8 blocks, right? And in the end, you see that already with this one, you can see that it's defined by just the first row, right? So now try exploding the C and the D and the E and the F into like, you know, U1, U2, U2, U1, and whatnot. And then you'll get like a dyadic matrix, which can equally be represented by just the first row, for example. Now, of course, this is a fully dyadic matrix. And what you can do is a similar idea. You can construct a quasi-dyadic matrix, right? By, for example, truncating this one to the first two rows, or anyway choosing a matrix that is like block by block, where each block is dyadic, but they're not necessarily part of the same matrix. Okay? So similar to the previous case. And what you can do is then look for how can I. So this defines a different type of action that is invariant with respect. Right? So the circulant one, what you want to be invariant is permutation that act block by block in a certain way. And here you can also create what is called like a dyadic permutation, which acts on the blocks in a certain way. And so when you choose your P, you're going to choose a P of this type, like we were doing before. And in fact, if you do this for a specific class of code in this work, which was introduced by Vysotsky and Barreto, also in 09, they start with a GOPA code already, rather than a Reed-Solomon code as a personal choice, but they were able to characterize exactly what happens, because remember, GOPA codes are defined by a bunch of elements and a certain polynomial, and then they figured out that if the polynomial satisfies this and this and this and this condition, then I'm going to get a code in dyadic form. Okay, and so what you want is exactly well, basically, you're going to choose your polynomial in a specific form and your signature in a specific form. And in particular, you have to have that the signature verifies this relation 1 over hi XOR j equal to 1 over hi plus 1 over hj plus 1 over h0. But this is the first initial element. So you start from the first one and then you generate the other ones bit by bit. So you start from h0, then generate h1, and then generate h2, h3, and etc. Okay, so in the end, what you're able to do is also similar to what we did before. So I'm not going to go to the key generation process in detail, but you start with like a full length GOPA code built using this relation, right? And then you select some of the blocks, permute them around, do your scale them with the diagonal matrix and stuff. Similar process, and in the end you end up with like a subfield subcode of the beginning one. Okay. So in fact, what you can do, for example, if you're interested in I'm not going to go through the whole process, but the GOPA polynomial, remember, is g of x, such that the support elements are not roots. In this case, g of x is defined as the product of x minus xi from 0 to minus 1. So it's a degree L GOPA polynomial, as we were expecting. L is always going to be our order, right? Like it was before the cyclicity order, now it's going to be the diacity order, diadity order anyway. And these xi's are exactly 1 over hi plus omega. This is chosen at random. So 1 over hi, for example, is the ith element of the signature. Omega is a random like offset, so it's just translated by. Okay, so it's all a bit technical, but you can see, like, for example, once you choose the signature, you can define these, which are basically the elements of the signature. They're all translated by the same. You're just translating them, and then this will give you your GOPA polynomial. Okay, and so you can see then that the elements alpha i's that form the support. Remember again, GOPA polynomial is defined by a bunch of elements of the support that are distinct, for which the polynomial is not a root, for which they're not a root of the polynomial. Then you can define them. Actually, it's defined in this way: alpha I plus 1 is 1 over hj plus 1 over h0 plus omega. Okay, that should be I suppose. Okay. So, I mean, obviously, I'm just telling you these things, but it's possible to verify. There's a big theorem behind it that says if you choose a dyadic signature in this condition, and then you form your support of elements in this way, and your GOPA polynomial in this way, then this is a GOPA code, but the matrix is dyadic, or quasi-dyadic actually, of order exactly L. Okay? And then once you start with that, it was more natural for Reed-Solomon codes, because Reed-Solomon codes are already cyclic. So you just like choose them so that they're not only cyclic but also quasi-cyclic. Here you have to do a bit more work to actually start with a parity check which is quasi-dyadic. But once you have that, the process at that point is similar, because what you do is just a selection, cut and choose, scale, subcode. Okay? At that point, so the idea is the same. In the end, you're going to end up with like an H over the base field, or over a subfield anyway. The most you can do is go all the way back to like F2, but also you can have like intermediate subfields that you use. This will be a parameter choice. We saw, for example, that in the previous case, the authors only did, for example, F16 over F2 to the 16 over F2 to the 8, so degree 2. They could have done like, but for some reason they did only the intermediate field. And here there was a different choice of parameters. And then you can use either H or G for your crypto system. Right? So it's all about the key generation, because once you have this, then you do Mc-Leese normally, for example, with your MG plus E, like you just code word, add the errors and stuff, and once you decrypt, what you do is you get this noisy code word, remove the transformation, and the trick is that you're able, by removing the transformation, to go back to the original code and use that one to decode, right? So you're not able to decode this code on the subfield, but because you know how the transformation was, in a way it's the same as taking off the P and the S, but it's a bit more complicated because your P was really like, a selection with the scaling and stuff. So you kind of like undo that, and then you're able to decode in the code original. So it's not as simple as taking a code and scrambling it, because you're doing a bit more work. But the overall idea is the same. So the encryption and decryption are pretty much the standard encryption and decryption of Mc-Leese or with the writer, right? But so what is interesting is really the key generation. And in both cases, you get really good results. Here, for example, they had some really good results. For example, if you choose something like Q to be 2 and then M to be 16. So again, you start from like F2 to the 16, but then you're projecting all the way on the binary. You can choose a code of length, say for example 3584 and dimension 1536, so about half as usual, and dyadic order 128. This will bring you to this many bits, so about 3 kilobyte. Okay, keep in mind these parameters are first of all more secure. These were tailored to have 128-bit security. The quasi-cyclic ones that we saw before were for 80, so that was 1 kilobyte. So then you start like matching and comparing, oh my works better than your work, whatever. But anyway, is it an improvement now? You can also change. So what they did is if instead you go to f to the 16 over f2 to the 8 like the other paper did. So you treat q to be 2 to the 8 and m to be 2, right? Then you get smaller parameters. For example, your code can be 1536 and 1024. So the ratio here is a bit higher than a half, right? But doesn't matter. And then your order is 256, and this leads you to smaller. I think whatever it's this one. So it's about 2 kilobytes, for example, right? And so you can really play around with this and then select the parameters accordingly. Obviously, for example, the higher this is, the more you're able to divide your key size, right? Okay, so this looks extremely good because at this point, when we have 1, 2, 3 kilobytes, we're basically in the RSA realm. And we have the advantage that, for example, the encryption is very fast. The key generation is more complex, right? So if you compare even just with RSA, intuitively RSA key generation is you choose the primes and then you're basically done. There's some work to be done, but it's not as heavy as doing all this process with the code, right? Clearly. In terms of decryption, the RSA decryption is the same as the RSA encryption. It's the same operation, you're just doing powers. So here we're doing a complex unscrambling thing, and then we run the decoding algorithm, which has a certain complexity. So again, the decryption is going to be slower, but you have, first of all, at least an alternative. And then depending on the use cases, this is a cryptographic perspective. In a lot of cases, for example, what you need to do is do this between two parties, like a server and a client. The server is the one that generates the key. So if I'm to communicate with him, the server has the key, and the client is doing encryptions, and the server decrypts. So key generation and decryption is the same person, and then encryption is another person. And so it makes sense, for example, to have something in which the encryption is fast, the decryption and the key generation are slower, but they are done by like the big powerful guy. Yeah. And also, like, for example, you do a lot. So the key generation you tend to do just once, and you can use the same key more than once. So it matters more to have a fast encryption than it is to have a fast key generation, in certain scenarios at least, right? Then depends what you're doing. So it's good to have an alternative like that. So this was all very promising, definitely a good idea. But obviously, the weak link is we have to make sure that this process does not break our security. And this is unfortunately what went wrong. And so, again, this is a very good tutorial for what happens in cryptography, is that there's this constant collaboration between cryptographers and cryptanalysts, and it's like two hands of the same person, really. So there's a new proposal, and then people analyze the security. Maybe there's a break, and then maybe there's a fix. And then in the optimistic scenario, I personally tend to prefer, actually, it's not good. Like, you should evaluate your security ahead of time, but sometimes it's hard, right? And then these people have definitely an expertise in seeing the weak links and analyzing and breaking stuff. So if it is a new proposal, and then it gets broken, and then it gets fixed, and at that point you're like kind of like more sure that that's secure. But of course, if this happens like more than once, then you're like, okay, maybe the idea to begin with was not so sure. Yeah. So in the ideal world, like, I propose a new system, no one can break it, it's great. But in the back of your mind, you're still like, okay, did they really go the full way? Did they really push it? Okay, but so it's debatable. But anyway, if this happens at most once, then like you can assess clearly the security is one thing. If then it tends to be so. What happened with this is there was an attack by Fougère, Otmani, Perret, and Tillich. So 4 researchers in France, which is where a lot of the code base coding theory, code-based cryptography gets done, which is simply now known as FOBT. And what they did is they simply, so the idea is kind of simple but elaborate at the same time. So remember what is like one of the most fundamental ideas of coding theory is that G and H define the duals. And in particular, for example, that H times G transposed is equal to 0. Okay? All right, so obviously, what you can do, this is valid for any parity check matrix and any generator matrix, right? And also, in particular, when you think about it, is valid for subcodes as well. Because if I have a subcode, whether it's a subfield subcode or a subcode chosen in another way, it will still make 0 when multiplied with H. Because it's just a subset of the words, right? H is saying, whatever you multiply by me gives me 0 for any code word. Now, instead of choosing all the code words, I choose only some of the code words, and they give me another matrix, but they still make 0, right? And yeah, so if you choose them so that your subset of code words, aka your subcode, is just characterized, for example, by having coefficients in the subfield, that doesn't change. And so what is curious is that you can, for example, if H is defined over F Q to the M and G is defined over FQ, that is still valid when you treat your operation over the larger field, right? You can always imagine that every operation you do on the larger field with elements from the subfield is still well defined and still works, right? So suppose you have elements in a finite field, for example, in F2 to the M, right? You have vectors like alpha, alpha squared, alpha to the 4, something like this. And then you, for example, do sums that are only binary sums. So instead of multiplying also by elements, you're also just summing them like with ones and zeros as coefficients. That still works, right? Because the characteristic of the two fields is the same. Yeah. So they're compatible. So it looks strange, but you actually can define the arithmetic properly between elements of FQ and elements of FQ to the M, right? And so basically, this equation is valid also for subfield subcodes. And now you can kind of see where we're going, because G, for example, is my public key, right? Which is the matrix over the subfield. And H is the one that the person uses to decrypt, right, to the code. So that is not known. That is the matrix of the father matrix or the mother matrix, or the matrix is feminine or not, right? So, so basically, you can really look at this as H has a certain shape that should be a specific one. For example, the GOPA one with the elements, or the Reed-Solomon one, right? Because that's what you use to decode. Remember that, for example, the Reed-Solomon and all the other codes, we defined them, they were in alternate form. So you always have them of the form y1, yn, and then x1, y1, xn, yn, and then x1 to the r minus 1, y1, xn to the r minus 1, yn, right? This kind of like Vandermonde times diagonal sort of shape. You use this to decode, right? So if you are able to find a matrix in this form, then you can decrypt, you can decode. So this is kind of like a secret key. And it may even not have been the original one that you had, because, for example, you only took some of these blocks and you moved them around. So, but it doesn't matter in the end. Like if you're able to find one matrix in this form, you can use it to decode. And so this leads me to an attack, because on the other side, what I do have is I have a matrix G, which will be like G00, G01, like you know all the elements of this is public. And so when you multiply this times that, you can treat these as unknowns and these as just coefficients, and you build the most classical of system of equations. So from this, basically this you can see as a system of equations. In the unknowns, these, right? And each equation is like one of the zeros in this zero matrix. Yeah. Cool. So this leads you to a system of equations. Now, what is particular about this? Because in principle, you say, like, why don't you always do this with Michaelis? You always have the G, and you can always look for the H. Yeah. Well, first of all, is that the codes chosen have a very recognizable structure. So you don't have like R by N different positions. you only have the x's and the y's. There's actually n variable x's and n variables. So you really have only like 2 n variables, right? And then you have, exactly how many equations you have. You have kn equations, right? So you have kn. Roughly, anyway. Okay. So the system looks like you're not going to be able to solve it properly. But the crucial difference is that, so if you were trying to do this for Michaelis without knowing anything else about it, it would be impossible to solve, or too hard computationally anyway, to figure out what a solution is. But now this is where the problem is. We know that this is not only in this form, but it's also, for example, quasi-cyclic or quasi-dyadic. So we are giving more information to an attacker that wants to do that. Okay? And so at a very high level, what happens is I can greatly reduce the number of variables and equations that I need to figure out. And then suddenly, my system becomes possible. So I can really think, and I'm not going to be too formal again, but basically my system, I have a bunch of xi and a bunch of yi variables that are these ones, right? And my system looks like this: gi0, y0, x0 to the j, plus gin yn-1, xn-1 to the j. And this is for every I from 0 to k-1, and for every j from 0 to l-1. Okay, so this is a compact way of writing the system of equations. And then you just basically try to solve it. And what you can do is that you can use some of the properties. Right? First of all, this is what we call a bilinear system. Because it's in 2 types of variables. So what you can do is, for example, try to solve for the y's, and then once you solve for the y's, you solve for the x's. There are specific techniques to solve the system. So then, of course, again, the attack becomes very complicated very quickly. But you use certain properties. For example, what you use in the quasi-cyclic case is that, or in the quasi-dyadic case, anyway, let's do this one, is that y jl plus I is equal to yjl. So all the variables in a block are the same, right? There is this repetition, and also, for example, that the x jl plus I plus xjl is equal to xi plus x0. They're just a repetition of the original x's and whatnot. These are stuff that comes out of how the code is built initially. So you can see already that, like, if this relation holds, then you can really reduce the number of x's, right, that you're looking for, because they're the same as the initial x's. And same for this one, so they repeat block by block. So you're greatly able to reduce the number of variables that you're dealing with. Okay. For example, in the case of the y's, because they repeat so much, the number of y's that you get, the number of variables y's that you get, becomes very small, even like 1 or 2. And then you can even just guess. Yeah. There's only like these many possibilities for them. Then once you have guessed the y's, then you get a system in just the x's. Then it's a much easier system to solve. You can apply standard techniques. Okay, so you have to be careful that this is out of the question. And in fact, see what happens instead that some of the parameters were very extreme. For example, here is a little table of what happens. If you count the number of yi's and the number of xi's and the number of linear equations only in the yi's, for example, is the first row, right? Remember that the first row was just the yi's, and then the second is xy, yi, and then there's x squared yi, and so on. Right? So if you just look at the first row, you get a bunch of equations just in the yi. And so here, for example, you have, in the quasi-cyclic case, n0 minus 1. Remember, n0 is the number of blocks that you have. And that's the same as the quasi-dyadic case. and the number of xi is like n0 minus 1 also here, whereas here is n0 minus 2 plus log L. And the linear equations here are k0. And this is the number of blocks, not the vertical one, but the number of blocks horizontal ones, the number of row blocks. So yeah, so you can see that your matrix is like k0L times n0L, right? If your matrix was k by n. Okay, so there's like n0 blocks this way, k0 blocks that way. And here instead is n0 minus m, where m is your extension degree. Is how much you project by. Okay. And so on. And so, for example, if you're just trying to solve this and this, right? If you're just trying to solve for the y's using linear equations in the y, then you have n0 minus m, and then n0 minus 1. So you just have, in total, m minus 1 things to guess. Because it's this minus that. It's n0 minus 1 minus n0 minus m. So the n0s cancel out, and you get m minus 1. Right? Mm-hmm. Now, if, remember, one of the parameter sets was f to the 16 or f to the 8. M is 2, and therefore m minus 1 is 1. You have exactly one variable to guess, and then all the other ones are going to repeat, and then it's going to be very easy to solve for the x's. Okay, so this kind of, in the quasi-dyadic case, for example, this characterizes the number of, the discrepancy between the variables and the equations. Of course, in the moment you have exact, you know this, everyone knows it from college algebra. If you have as many equations as variables, you can solve the system right away. If you have like one more in this case, you only have to guess one, and then like you can solve the system. Right? And so you kind of want this to be big, for example. In the quasi-cyclic code, they were kind of, I mean, also you have to like guess some stuff here. You have n0 minus 1 minus k0, but n0 and k0 are very close anyway. Okay. And actually it's worse because n0 and k0 are always very close because n and k are kind of like in 1/2 ratio always. So there's not much you can do to mitigate that. Whereas in the quasi-dyadic case, you can actually at least play with the m. You can say, oh, if I take a code and bring it all the way down to f2, then my extension degree is, for example, 16. Well, then this is like already 15 variables that I have to guess, and then there's some effort in there. Okay, and so what happens at the end of the day is that the systems were broken dramatically. For example, the parameter set here, that we saw here, was broken in about 0.06 seconds with a basic C implementation. This was estimated to be about 2 to the 18 operations. So that's obviously a disastrous, compared to like the 2 to the 128 that you were shooting for, or 2 to the 80. I think this was aiming for 2 to the 80 anyway, right? But in this case here, you can see that, for example, you have n0 equal 9 blocks, right? We had it here, and that gives you exactly, after reducing the system, there's 3 variables of the y type, and you're just able to guess that quickly and then solve from there. Okay, and all the other parameters in the quasi-cyclic proposal, because they all use this kind of like very small degree, they were all broken between like 2 to the 18 and 2 to the 20 operations. So ranging from 6 milliseconds to 8 milliseconds, something like this. Actually, no, not milliseconds, like centiseconds. 600 of a second or 800 seconds. Okay, so that was pretty much doomed right away. And what happened with the dyadic proposals is instead that like these proposals were more resilient than these ones. Right? Because you can look at the m right away there. So these proposals with the m equal 2 were also broken in a similar amount of time, like 2 to the 14 operations or something like this. For some of these ones, the attack kind of increased to something like 2 to the 34 operations or bigger. So now this starts to be a little bit more challenging, but definitely not impossible. So this actually I'm referring to. So actually, what is good is that we had several different types of parameters for the dyadic variant that were using m equal 2, m equal 4, all the way down to like m equal 16, right? Because what they did is they started from f to the 16, and they say, okay, let's project all the way. So let's project over F2 to the 8 first, then over F2 to the 4, and then like this one were the binary ones. These were the binary codes, because you project all the way to the base field. These ones were not being able to be broken. In practice, at least, they were not being able to be broken with the sample implementation that they had, which is really, because I've seen it, a script that you write. I mean, at this point, you put it down in C or Python or whatever you use, and you just run it on your laptop. Right? And so if you run it on your laptop and it takes 0.06 seconds, it's bad, right? But if you run it on your laptop and it doesn't work, then you can either try to run it with more power, or just say, okay, look, I can't do this because the complexity must be something like 2 to the 40 or 2 to the 50 or 2 to the 60, and clearly that is not going to be run on a normal computer or classical computer anytime soon. It's still way below what you claim, but it's not verifiable in practice, right? So then at that point you have to kind of like figure out, okay, can I find a complexity formula for this and analyze all the moving pieces? And that was kind of like hard. But they figured out that anyway the attack kind of scales proportionally to the M. And for something like M equals 16, it was already out of what you can run on like a normal computer. For up to M equal 8, as I said, here it was like 0.06 seconds, and here it was kind of like 30 minutes. Okay, and then as you know, exponential growth, it scales very quickly. So of course, if you take M equals 16, already you cannot run it. And maybe if you take M equal 25 or something, then you're safe. But until you have a precise complexity formula, you cannot accurately estimate this. And so part of the problem after that was like, okay, this is seriously broken, but maybe there is still a hope if we can play with this extension degree. And what we try to do is exactly that. But then, of course, what happens as a result of this is that you tend to increase all the parameters, because you already remember that even from this simple example, when we take the small extension case, we had something like 2 kilobytes, because the code is much shorter, even though your code is defined over F2 to the 8, so you're actually giving finite field elements, which are bit strings, right? So your code is defined with like larger elements, but it's much, much shorter. Here you have a binary codes, but you have like twice as many. So in the end, you get like bigger parameters, right? And then you want actually your extension degree to be bigger, your length gets even bigger, and the code that you get out is not as good as what you had initially. Okay, so there is still a significant reduction, but now it's not 2 or 3 kilobytes, it becomes like 8 kilobytes. Okay, it's still kind of meaningful, but then you have to be like, okay, maybe we kind of like fix it. Oh, there is this problem. These guys found it. There is a complexity for the attack, and then like, okay, that's where we can get 8 kilobytes. Okay, people are happy. But then that's not what happened, because then people fixed it, and then like there were more attacks coming out using different properties. And then like, okay, now I have to stay out of attack A and also attack B. Yes, I can do it, and then you keep increasing. So after a few years, there were attacks and fixes on back to back, and the keys and the keys started to get like bigger and bigger and bigger, up to like, I don't know, 18 or 20 kilobytes in the end. And then people lost both confidence and kind of interest, because of course 18 kilobytes is better than the 65 or whatever. Actually, for a comparable level of security, McLeese goes up to like 200 kilobytes or something really big. So 18, of course, is better than 200. But one is unblemished, and the other one has been blemished many times. Yeah. And so in the end, like, you really want to be sure that your first of all, cryptography needs to be secure after practical. Right? You don't want to have something that is fast but not secure. That doesn't make any sense. So this kind of approach was interesting, but unfortunately, not as promising as it looked at the beginning. And if you think about it just at an intuitive level, because of course we did this, I mean, at a very intuitive level anyway, right? Because we don't have the advanced mathematical tools anyway for this, but you're taking some algebraic codes which are very structured already, and you're putting even more structure, so it looks like you're giving a big arsenal to an attacker. Mm-hmm. And then that seems dangerous. People just don't trust it very much. But the overall idea was not bad of using structured codes. I think maybe it was just bad ingredients to begin with. And so what people started doing, and that's what we will see for the rest of the lecture, is use different codes that maybe have less structure. And who better than LDPC, which stands for low density parity check. Okay, so LDPC codes are a particular type of codes. Do you have questions? No, you good? Okay. So I just want to. So basically, okay, what is an LDPC code? These are not algebraic codes like all the ones that I would like to see more, but like we only give an intuition of like how to build Hamming codes, BCH codes, and then like all the other codes are built kind of using the same tools. Like basically, you have some elements and some polynomials and some stuff, some relations between them, and you build a code. The code is like a big network connecting all these intertwined properties. So the decoding is what? Is basically like relying on a certain key equations that you, once you solve up to that many errors, is basically like the equation is like up to a certain degree, you can solve it, you can decode uniquely. Okay? This is a very different approach. This comes from engineering. And the idea is, look, it says here, is a low density parity check matrix. So the idea is that your code is defined uniquely by the fact that H is very sparse. So there is no algebraic component there other than your matrix is like 1, and then a lot of zeros, and then like, oh, there's a 1 here, and there's like a lot of zeros, like there's a 1 here. Okay, it's like a very sparse matrix in the sense that it's very few ones and a lot of zeros. So these are binary codes, and the only property is that their matrix is very sparse. And when I say sparse, technically it's something like O1, which means constant. And for engineering purposes, obviously the easiest way to do this is you choose the weight of each row, the Hamming weight of each row to be exactly the same, but it's something like 10 or 20 or something really small over a code that is long 1,000, okay? So that it's very, very sparse. Mm-hmm. So each row is exactly like 10 ones and like the rest are zeros in different positions. There is a strong connections with graphs. I don't know how much of graph theory you've seen. But these codes are connected, so basically each of the one is like a node in a graph and whatnot. Okay? But there is no, you see, there's no algebra behind it, there's no finite fields or anything. It's just binary codes, characters. And so what do you do with these? Because how do you decode them? And then what you can do with these is you can decode them. There is a decoding algorithm. There's more than one decoding algorithm. They all exploit this sparsity, right? And these decoding algorithms are usually known, for example, like bit flipping is one of the most popular ones. Right? And bit flipping is a very intuitive name. All these algorithms are probabilistic and iterative in nature. So again, they're not based on, for example, take your GOPA code or something. Oh, that's a bunch of elements tied up with the fact that there are no roots of this parameter. So when you multiply a received word, then like all these finite field elements satisfy some sort of intertwined properties and stuff. Then you like solve this key equation. And well, remember, like we did for the BCH, like oh, you have this quadratic, you solve it. Similar idea, but it's not quadratic, right? None of that. You're just taking a received word. So what you do in practice is this. Let's see if I can make it. Let's see if I can make it easy to understand. Essentially, you start with your parity check matrix H, which is sparse, and you get a syndrome, which is H times E, and you want to find E, right? That's equivalent to decoding. So what you do is, for example, you initialize E equal to the 0 vector, and we'll just try to guess where the error bits are. So it's probabilistic, right? And then start with like S prime to be exactly S. So we suppose we start to like a correct case, and let's start to see where the error bit is more likely to be. Mm-hmm. So this is probabilistic nature. Where is it more likely to be, the error bit? Where you find more matches between the syndrome and the columns of the parity check. Okay? And so what you do is simply this, something like while S prime is different from 0, right? You fix a threshold, like tau, for example, and up to that threshold, and so how you define this threshold is actually depending on the characteristic of the code. How many ones do you have, and like what is a reasonable threshold? And then you just compute essentially Hj times S. So you're trying to match the syndrome with the column of the parity check matrix, right? So Hj is the column J, right? And if you do times, what is the times between two vectors is like, it's not a standard operation, right? Because you know the vectors are dot product. You just map each, you just do like a component by component multiplication, right? Yeah, it's called star product. So that's kind of like an asterisk thing. So it's a vector that results in like component by component. Yeah. So if you have A0, AN minus 1, B equal B0, BM minus 1, then A star B is A0 times B0, and then A1 times B1, okay, and so on. This is a component. But why do we care about this? Because then, of course, these are binary vectors, right? Both the HA and the S. So you're only going to have a 1 if they're both 1 in their position, and you're going to get a 0 otherwise. So what this tells you is that if you look at the Hamming weight of this, right, that tells you exactly how many matches you had between the ones in the column and the ones in the syndrome, right? And so if this is particularly high, then you probably have an error there, okay? So you check whether this is essentially larger than, say, tau times the weight of Hj, okay? That would mean an unusual number of matches, okay? So you see why tau is this threshold, because like if I have more coincidence of ones in many positions, then probably there was an error there. If it's below the threshold, I will discard that. So it's a probabilistic, if you want, this is what is called like a majority voting. So what's the most likely place? So you get like a bunch of candidates. And so if that happens, you just say that probably Ej was an error position. And you just set it to be 1. Okay, so it's kind of like in pseudocode form. And then what you can do is then you just regenerate the syndrome as prime Bs minus He. Right? So then you take off those ones. You're like, okay, I determined that like this and this and this and these positions are very likely to have an error because they have like many matches. So then I update my initial error vector contained only zeros. Now I know that like that one is a 1, that one is a 1, that is a 1. Okay, I didn't really reach my target weight, so I will just do it again, and now I expect to have less matches. But by doing this, I'm taking off the positions that I already have determined. And then I kind of iterate this, right? Until I get my target weight in E. So until I reach my E to be of the correct weight. So it's a probabilistic algorithm. This is kind of more subtle, at least was for me anyway, because I don't come from engineering, and probability was never my forte anyway. But the idea is intuitive, and is probabilistic. Every time you iterate, you take some decisions, and eventually it's going to be going and convert and find the correct error vector. Okay, so it's kind of crazy because it doesn't. I mean, to me at least, it doesn't exploit any hidden properties. It's just the fact that the matrix is so sparse that you're likely to have these matches only where the error happens, because there's a big distance between the columns. Now, of course, there are some good things about this and bad things about this that we'll try to summarize. And so, where should we start? So the good thing is, these are very easy codes to encrypt, because the multiplication is, you can encrypt in the same way, right? Vector times matrix, and it's binary, so it's kind of like, in that sense, same as GOPA. It shouldn't be any worse, because if you take a binary GOPA code, it's the same thing. It's like a binary matrix, interesting. Okay. When we look at how these codes work, of course, there has to be sparsity. So the codes tend to be quite long and big. So you wouldn't use LDPC codes by themselves, right? Because they would be like 20,000 long or something. Compared to the length they used to see for the traditional Galapagos were like 1,000, 2,000. Remember the sample parameters, they're much bigger. So there is no point, but you would tell me like, look, okay, I have nothing interacting with this, right? And in fact, when you think of structural attacks, right? When you think of structural attacks, what the attack used was the fact that h times g is equal to 0, which is common to any linear code, so even these ones, but h has a very recognizable shape. And then you put more structure on top of the h, so it becomes like really easy to do like sort of like an algebraic system sort of thing. Here, what you're trying to do, you only know the h is sparse, right? So you have no algebraic system to build in the first place. What does it mean that h is sparse? It means that h, remember, defines the dual of the code defined by g, right? So if h is sparse, then the dual of g contains many low weight code words, right? Because the columns of h are the rows of the dual and blah, blah, blah. So what the only thing you know is that the dual of g is given to you, so its dual code contains many low weight words, and very low too, like very low. Okay? So what you can do instead of building a system of equations that you don't have any appeal for, you can try to look for low weight code words in the dual. And it's pretty easy to see that that is basically the same as decoding the dual. Okay? But that is a good thing, because essentially what you do is, again, ISD. So you can try to run ISD on the dual, and if you find enough low weight code words, then you reconstruct the H. Make sense? Because you're trying to find the code words in the dual, those are exactly the columns of the H. Or the rows of the H, anyway, dependent, you know. So, but again, that's a good thing, because we know the ISD is exponential. And now we have a unification. So even from a cryptographic point of view, before we had two pillars. My matrix needs to look random, and then in a random matrix, my decoding is hard. One is the structural, one is the decoding hardness. Now they're actually one and the same. Because even the structural weakness is only weak if ISD is efficient. Okay? And so you bring two problems into one, and it's the hard one, it's the one we want. So from a security point of view, these codes are strong. Of course, if you take 10, this is not going to be very challenging in a cryptographic sense. But so these codes were then evolved into what now we call MDPC, where M stands for moderate. So what you can do is, instead of taking a constant row weight, say equal to 10, so very low, you take your weight to be, for example, square root of n. Okay, which is still much lower than the length, but not dramatically lower and not constant. And you can still apply the same algorithm. Of course, it will not work as well, right? So you lose some performance, but you have a big increase in the weight. And so now these kind of attacks, when you try to run them on the matrices as structural attacks, they're not so easy. Yeah. So by doing this, you basically bring your ISD to attack the key on the same level, or your ISD to actually decrypt your ciphertext. And then you really have like one and the same. And then you can really claim these kind of codes are secure with the same type of attack, both in key security and one-way security, for example. And that is a really good thing, right? And because of that, also it means, and this is perhaps the most appealing thing, that if you want to add, for example, QC, you can do it, and it's not going to affect. So instead of having a sparse matrix with like very few ones and lots of zeros, you have it in a specific way. Okay, it doesn't change anything because you're still trying to do ISD on it. Mm-hmm. So instead of sampling this matrix entirely at random, for example, you can sample it in this way, right? And here is just like very few ones and like a lot of zeros, and here's like a few ones and a lot of zeros, and then the remaining are just the circulant ones. So you can easily get an LDPC or MDPC code in quasi-cyclic form. All you need to start with is the vector that has very few ones, and then like all the other rows will have the exact same weight. And that doesn't change the nature of this, okay? That is not entirely true because technically you do get a speed up, but that is not major, okay? I mean, you get a speed up in the fact that you know that the next rows of the parity check were generated by the first ones, but you're still looking for decoding in the end, okay? So you lose a little bit of performance, you lose a little bit of speed, but it's still manageable, okay? So what is good then is that you can take these codes. You wouldn't take the whole codes, but you can now do them QC, and they're not subject to the type of attacks that afflicted all the previous proposals. Okay, so this is a very good resource. Of course, nothing is perfect. So what we have to deal with is the fact that these kind of algorithms are probabilistic, right? And with this kind of majority voting algorithms, what happens is that if you make all the correct decisions, then at the next step, you're more likely to be successful, and then more likely to, and then you'll get to the correct vector. But if you start with like even just one or two bad decisions, then the error propagates. And then so you have a very small chance of actually what is called a decoding failure. Which means that the pattern of error that you were looking for was legit, like up to the correct weight and everything, but because of how the things were presented, during your decoding algorithm, you made a wrong decision, and then it went off the rails, and then your decoding fails. So it's something that you should have been able to correct, but it fails. Algorithm return fails. This is kind of something that we expect for probabilistic algorithms. It was not the case for algebraic decoders, because algebraic decoders is really solving the equation, right? Those are the roots of the equation. I mean, once you do that, it doesn't matter, right? So, but in this case, there is a small probability, and we're talking something about, depending on how big the code is and how the shape of it is chosen, something like 10 to the minus 7, for example, which is like 1 in 10 millions. Okay, so this is what we call the decoding failure rate, or DFR. Now, if it's 10 to the minus 7, you would say, it's so small you can ignore it, right? False. Because 10 to the minus 7 is something like 2 to the 20, 2 to the 30, right? And so that is something manageable in terms of cryptographic operations. You can run it, and eventually, if you run enough time, so suppose that this is 2 to the 20, which is kind of appropriate because like 10 is like 2 to the 3 more or less, so something like that. Suppose this is 2 to the 20. Well, I can run 2 to the 20 operations even on my laptop. And in fact, I can run it if I want in parallel or many, many times. So people are able to run these kind of operations many times. And if you do it 600 million times, you can do it with the simple script that you do. And what you do is that every 10 million ciphertext that you submit, one of them will fail to decode. And that intuitively tells you something. Tells you, oh, there's a problem here. Because where these decoding errors happen, they're based on how the columns of the matrices are situated. And so you do this many, many times. So this is a type of attack. Of course, remember we discussed the types of attacks, right? It's not going to be a CPA attack, but if you do a CCA attacks, where you're able to like look at many ciphertexts and ask for decryptions, then you can actually do this kind of analysis. And in the end, it's quite sophisticated, but what you can do is you can reconstruct the exact, what is called distance spectrum of the code. So slowly but surely, I think the original number was something like this, 356 million ciphertexts analyzed, and in the end, they were able to map out the distance between all the coders. Of course, once you can do that, you can decode. And so that is a CCA attack. This particular type of CCA attack is called a reaction attack, because you just look at the decryption of ciphertext and then you react accordingly. So you're basically trying to feed malicious ciphertext and see which ones of them fail to decode, and eventually you will extrapolate like, oh, that position is a bad one and whatnot. So because you open the door to an algorithm that is not, a decoding algorithm that is not exact or is probabilistic, no matter how small the probability of failure is, you can exploit it. So how can you address this? How can you address this? Is to make this big. Now, if you make this 2 to the 80, then there's no way to get even a single decoding failure, but that number is huge. So for that, you have to enlarge your code a little bit. The parameters are not as good as the original ones. Basically, this kind of addresses it, except that it gets increasingly hard to make this algorithm precise to that point. So what people have been trying to do over the years is not the standard bit flipping, but try to do more sophisticated version of this probabilistic algorithm. So that, for example, instead of taking decisions black and white, like, oh, this is probably an error, this is probably not an error, you do some sort of like gray area in which you select some positions that are most likely, and then you kind of like check them again, and then you either discard them or confirm them at a second run, right? So, of course, again, there's no my area of expertise, but you can improve these decoding algorithms to the point that hopefully they give a decoding failure, which is always going to be non-zero, but you want it to be as small as possible, possibly negligible, and then at the point you can use these codes to really good effect. So in the end, just to conclude, what you do get is that if you choose, for example, your size to be something like 1200, something like this, and then you choose like rate 2, or actually rate 1/2 code, then it's just 2 blocks like this. Then your length is 2p, so it's kind of like length 24,000, right? And you get in the end something like 3 kilobytes again. And that is back to kind of like where we wanted to be, with a completely different approach, but more promising because it looks like we're safe from algebraic attacks. We can use this cyclic structure to our advantage, or this quasi-cyclic and quasi-cyclic structure. We have some annoyance with the fact that we have occasional failures, and that's not just a detail, but it can become a big problem. But we can still use this approach to good effect. And in fact, these kind of codes now are at the forefront of the whole coding theory-based approach. So when you think about code-based cryptography nowadays, with the whole post-quantum thing in mind, and I don't know if I did mention this to you or not, like these codes are about to be standardized, this crypto system, but there is a process for that. The two big competitors in the process for the code-based type of crypto systems are either the original McEliece approach with the binary GOPA codes, which has been unblemished for 40 years, and then you're just gonna bite the bullet and take the big key. So you know that you're gonna be using this on the internet, but not on the smart card, or in your tag, or nowadays, it's an increasingly less serious problem because even like your phones and Apple Watch can probably handle what is like 250 kilobytes of key. Not a big deal, but of course, like there are, Internet of Things and the cloud and other stuff that strongly depend on the small communication factor. In that case, the other main competitor is represented by schemes that are based on MDPC codes. Okay, and so this covers like one area, and next week we will see another area. There is now 4 or 5 different areas that use this kind of different approach. Right? The traditional approach from number theory-based public cryptography, the one from RSA and discrete logarithms and stuff, was cute. It used very strong number theoretic ideas like factoring is hard, computing is hard, but it's very structured. And Shor's algorithm just put all of that in the trash because it's able to dissect. I think we did discuss this. Shor's algorithm is able to dissect groups and find orders of elements in groups, and everything related to that is out the window. It becomes polynomial time on a quantum computer. So now we're doing this for crypto systems based on problems that do not suffer from this. So there is no polynomial time quantum algorithm for these kind of things, like decoding, right? And so there is these ideas that are similar to this. So this kind of concludes our part. I think it gave a good overview of what code-based cryptography is. It's based on linear codes. It all kind of revolves around the idea that decoding is hard if you can hide your code, or in general, if you try to decode a random code. And so then, of course, you see how much research comes out of trying to put the details in place. Similar thing we will see next week on different lattices, which is a similar thing. Okay, excellent. Great to see you here.